Commercial aviation is governed by a strict physical reality, the massive weight-to-power ratio required for flight. Every pound of fuel must justify its presence by delivering maximum energy output. Forcing hundreds of thousands of pounds of metal off a runway requires a propulsion system capable of generating immense, sustained thrust. Current battery technologies cannot meet this requirement. A battery array capable of lifting a modern long-haul airliner would be so heavy that the aircraft could never leave the ground. For heavy aviation, energy must be stored in the high-density chemical bonds of liquid hydrocarbons. To maintain these liquid fuel advantages without fossil extraction, the industry is turning to the power-to-liquid, or PTL, pathway to produce sustainable aviation fuel. Power-to-liquid serves as an energy storage mechanism. It is designed to capture intermittent electrical energy and lock it into a dense, stable liquid form. The process follows a specific chemical logic, combining renewable electrons, carbon dioxide, and hydrogen to synthesize jet-range hydrocarbons. Because pure hydrogen is not readily available in nature, the system must first generate it by splitting water molecules using a portion of those renewable electrons. Executing this equation requires a precise 8-step industrial energy chain that moves from raw electricity to a finished high-performance fuel. Mastering these 8 conversions allows the aviation industry to utilize the energy density of liquid fuels while replacing the carbon source at the beginning of the chain. This process begins at a specialized facility where renewable energy generation and chemical synthesis are integrated into a single continuous flow. In Step 1, solar arrays and wind turbines harvest massive amounts of electricity. This power is intermittent and difficult to store at scale without a chemical carrier. Step 2 involves routing this raw electricity into industrial electrolyzers, which serve as the first major transformation point in the chain. On a process flow diagram, water meets electricity inside the electrolyzer node. The electricity provides the energy needed to break the chemical bonds of water, liberating oxygen and hydrogen. The hydrogen is isolated and pushed forward, acting as the primary energy carrier. While hydrogen carries the energy, jet fuel requires a stable carbon structure to remain liquid and stable at room temperature. Step 4 introduces carbon by capturing carbon dioxide from an industrial emissions source or the atmosphere. Using captured carbon allows the fuel to operate within a circular carbon cycle, rather than adding new CO2 to the atmosphere. With reactive hydrogen and stable carbon dioxide secured, the facility has the necessary building blocks, but it must now overcome the primary engineering challenge, synthesis. The facility must now force these separate streams of hydrogen and carbon to merge into a single complex molecule. Step 5 occurs inside a synthesis reactor. Using specific catalysts, the facility converts the raw feedstocks into intermediate molecules. As hydrogen and carbon dioxide converge in the reactor, the molecules rearrange into new groupings. The output of this reactor is either syngas, a mixture of carbon monoxide and hydrogen, or methanol. These are precursors for building heavier fuels. These schematics show the new molecular structures. The carbon and hydrogen are now bonded, creating a stable platform for the next stage of growth. In Step 6, these intermediate molecules are fed into a secondary reactor to begin a process known as polymerization. Polymerization involves linking these short intermediate molecules together, end to end, to create long hydrocarbon chains. Small clusters of carbon and hydrogen snap together in a rapid chain reaction, forming the long, undulating structures characteristic of heavy liquid fuels. Engineers control this reaction to ensure the output falls within the jet range, specifically chains between 8 and 16 carbons long. The intermittent energy originally captured by wind and solar is now physically locked into these dense, stable liquid chains. While these long-chain hydrocarbons contain the necessary energy, they require further refining before they are ready for commercial flight. Step 7 is the upgrading phase. Here, the raw synthetic hydrocarbons are isomerized and refined to meet exact technical standards. This process tunes the fuel's physical properties, specifically ensuring it has the correct energy density and a freezing point low enough for high-altitude operation. This precise molecular tuning is what allows the fuel to meet the rigorous safety certifications required by international aviation authorities. Once the fuel is certified, it moves to Step 8, the final deployment from the chemical plant to the airline. Before reaching the airport, the synthetic fuel is blended with conventional fossil-based jet fuel. Blending is currently a regulatory requirement for commercial airlines. It ensures compatibility while the industry scales up synthetic production capacity. On the diagram, fuel leaves the blending tank and is delivered via existing pipeline infrastructure directly into the aircraft. This drop-in fuel requires no modifications to the aircraft's engines. The energy is delivered in a form the hardware already understands. The process is complete. What began as electrons and raw gas has been transformed into a standardized, commercially deployable commodity. We can now trace the unbroken chain of energy transfer from the first watt of renewable power to the final thrust of the jet engine. The full 8-step process flow diagram shows every stage of this conversion working in a single synchronized loop. Energy is harvested from the sun, stored in hydrogen, bonded to a carbon backbone, and finally refined into a dense liquid. The chemical accounting balances. By substituting the inputs, we arrive at the same high-performance result as fossil fuels. This 8-step model is efficient because it concentrates the chemical complexity at the production facility rather than on the airplane. By producing a liquid hydrocarbon, this pathway utilizes trillions of dollars in existing global infrastructure, from fleets of tankers and long-distance pipelines to airport fuel farms. This avoids the logistical hurdle of redesigning every aircraft in the global fleet for bulky hydrogen tanks or massive battery packs. These synthetic fuels deliver the exact energy density required for high-performance turbines to operate at their maximum thermal and mechanical limits. The power-to-liquid pathway allows the aviation industry to transition its carbon source from subterranean fossil reserves to a circular loop of captured electricity and atmospheric carbon.